60. Gewonnen hat Herr Dr.
Holy cow, have you ever seen anything like that? It looked like some big invisible Godzilla just stepped all over that train car. But it wasn't invisible Godzilla at all. In fact, it was simply air pressure. Air pressure, you see. Mr. B, how could air crush a train car? Well, that's exactly what we're going to talk about today in the second objective of our Ocean Climate Weather Unit. And so we want to get out the matrix that you have and take a look at it. We're going to be focusing on this second part right here in the center of your matrix. And our objective today is to identify how local weather is affected by high and low pressure systems. And you're going to be answering a few questions here, a few essential questions, and taking a few notes and understanding what air pressure is, how it affects us, and how it affects our local weather. But to understand more about what air pressure is, I want to show you another quick, it's like a 3 or 4 minute video, but it's pretty good at explaining air pressure and its effect on us. Alright, so let's take a look at this.
You may not realize it, but from the moment you got out of bed today to the point where you sat down to watch this video, you've essentially been swimming. Why? Because air is a fluid just like water. It has waves and eddies, it flows, and when you push air out of the way, it rushes around you into a wake. So why don't we notice it most of the time? We commonly think of air as empty space. But while 1 cubic centimeter of interstellar space, the volume in the tip of your pinky finger, contains roughly 1 atom, the same volume of air has about 10 quintillion molecules. If that sounds hard to wrap your head around, it happens to be about the same as the number of insects alive on the planet, all crawling, climbing, and flying over each other in an enormous, tightly packed swarm. When this swarm of molecules runs into things, it exerts a force, pressing against the boundaries of the fluid like water pressing against the glass of a bottle. This is known as air pressure. And while air is lighter than water, all those molecules still get pretty heavy, with the total air filling a typical school gym weighing about as much as an adult elephant. So when you walk into a gym, how come you're not immediately crushed by the elephant of air in the room? Well, first of all, because most of it is pressing on the floor and the walls, and the part that is pressing on you is pushed back by the pressure inside you. You see, the air, as well as the water and everything else that fills our bodies, exerts an amount of pressure equal to that of the air outside. Of course, this is no accident. It's precisely what allows us to survive in the normal atmosphere, and what makes it more difficult at high altitudes or deep water. And we normally don't feel the air pressing on us because it's generally uniform. So even though different amounts of air molecules are hitting you at different times, the swarm is so thick that all those little differences average out. What happens when air pressure isn't uniform? This means that the molecules are pushing harder in one region of air than another, driving the airflow from the higher pressure region to the lower. We feel this flow directly as wind, and the pressure systems that meteorologists are always going on about are responsible for other weather changes, from the mundane to the catastrophic. But differences in air pressure do more than just let us complain about the weather. They're the very reason we're alive. We breathe by lowering the pressure in our lungs, allowing air to rush in. So the next time you take a deep breath, think of the unfathomable number of air molecules you're commanding to move. We look up at the night sky to ponder the infinity of space. But unless you're watching this video from that deep space, there are more air molecules in and around your body than there are grains of sand in all the world's beaches and deserts, stars in the visible universe, or both of those numbers combined. The vastness of the universe is right in front of you and inside you.
Well, alright, I hope that video helps you to understand what air pressure is just a little bit better. We're going to dig into that a little bit more, try to simplify things a little bit. And I think to get started, even though this is not in your matrix, we ought to define what air pressure is. So find some space on your matrix, maybe on the back, that type of thing, and let's write down the definition of air pressure. Air pressure, if you look at this definition here, air pressure is a column of air that pushes on everything from every direction. So if you can imagine a column of air coming down from the top of our atmosphere to where we are on the planet, and all of that air pushing down on or towards the planet and in every other direction, that would be air pressure. Also, you'll notice in this column that as you move up the column of air, it becomes less and less dense. The closer you are to the planet, the more dense. And that would make sense, because as air pushes down, it crunches the air molecules together till they get closer and closer, closer and closer, till you get down to where we are on the planet, where they're very close together. So that's the definition of air pressure. Now let's talk about something that has impact on air pressure, and it kind of goes back to the definition, and that is elevation, how high you are. If you climb to the top of a mountain, it's a lot harder to breathe than it is at sea level. Why? Because there's more air at sea level. The higher you go in elevation, air pressure decreases because there's fewer molecules. There's less pushing on them, so they're not as densely packed. The closer you get to sea level, the more densely packed air becomes. And so one of the things that really affects air pressure is elevation. That's why when you get an airplane and you go up really high, like 37,000 feet or something like that, your ears pop. And it's because of the change in air pressure. It's much thinner. The air is much thinner in the higher altitudes than in the lower altitudes. Okay, so now let's take a look at your matrix, and let's talk about how changes in air temperature affect density. Elevation affects air pressure, but let's talk about how changes in temperature affect the density of air and what impact that has on air pressure. Now this is kind of a review from the awesome lesson that Miss Hijik gave us in the first objective, as we talk about the density of air. Cool air is always going to be more dense. Cool air is always going to be more dense than warm air. And the reason is because cool air, this is a review from our first matrix, when air is cooled, the molecules become, they get closer together, they move slower, they become more dense. Well, things that are more dense have a tendency to sink. And so cool air actually sinks. More dense air actually sinks. This creates high pressure, because as the air sinks, it's putting pressure on the planet and anything or anyone else that's on it. And so cool, dense air has a tendency to create high pressure systems. Whereas warm air, the molecules are further apart, it's less dense, and so the air has a tendency to rise. And so because it's rising, it's not putting pressure on the planet, and it causes more low pressure systems, or a low air pressure systems. Now this answers the first two questions in your matrix, which describes a change in how changes in air temperature affect the density of air, but also how these high and low pressures are formed, because that's it. When the temperatures are cooler, you typically get more high pressure systems, and when the temperatures are warmer, you typically get more low pressure systems, because of the dense air has a tendency to sink and the warm air has a tendency to rise. So that kind of goes into how these high pressure systems are formed. All right, so now let's take a look at how these high and low pressure systems affect our weather. Because cool air has a tendency to sink, and in high pressure systems air is sinking, not rising, there's not as much opportunity for moisture to rise from the earth into the air and condense, forming clouds and possible rain and that type of thing. And so typically in a high pressure system, because that air is sinking in a high pressure system, you typically have more calm, clear, and sometimes cooler weather. Yesterday was a high pressure. It was cool, it was clear, it was a more high pressure system, and the air was sinking. Now, the opposite would be in a low pressure system. In low pressure systems, the air is less dense, and so it rises. And if there's moisture, then it takes that moisture with it. as it rises, and we call that evaporation. And I know y'all have had that in the water cycle before, but that's what it does. And as that air rises and cools, the water molecules begin to condense, and that's where you get your cloudy weather. In these low pressure systems, because hot air rises and takes water with it, you have the potential to get cloudy weather. You could have possible rain showers, even stormy weather. And so that's how high and low pressures have an impact on our weather. Again, typically, just to review, high pressure systems is typically calm and clear. Low pressure systems, typically cloudy, possible rain showers, even storms. Now, let's talk about how high and low pressure systems help to form winds. Wind formation. Wind occurs, if you want to read this definition, you might want to write this down under that fourth essential question there. Under the fourth essential question, wind occurs when air moves from high pressure systems to low pressure systems. Think about it. Air wants to move from areas of high pressure to areas of low pressure, much like a balloon. Think about it. When you blow up a balloon and you don't tie the knot and you just let go of it, the pressure inside the balloon is greater than the pressure in the room that you're standing in. And when you release the balloon, that air wants to move from high pressure inside the balloon to low pressure outside. And as it does, the air moves out of that balloon. You can feel it. And that's what's happening when wind is formed. You have an area of high pressure where the air is pushing down on the planet with a lot of pressure. And if it's adjacent to an area of low pressure where the air is rising, those air molecules want to move from that area, just like the balloon, move from that area of high pressure to the area of low pressure. And that movement is what we call wind. So again, wind is wind. Wind occurs when air moves from areas of high pressure to areas of low pressure. And the greater the difference, and this is just a small note, the greater the difference in pressure, the stronger the winds. If my high pressure is really high and my low pressure is really low, I can get really strong winds. And if they're pretty close together, then I might just get a gentle breeze. Okay, now let's talk about how scientists measure air pressure. They measure air pressure with the tool they call isobars. Now, isobars are lines on a weather map that connect areas of equal pressure. I don't have any lines on this weather map. All I have are air pressure readings. We get air pressure readings from what we call a barometer, and the barometer reads air pressure in a particular area. And so these numbers represent areas of pressure. You'll notice here there seems to be a line of air pressure at 1016. Here you see one at 1020, and watch. This line seems to curve around and kind of form a circle. And then inside of that circle, you'll notice there we go up to 1024 with another circle. Over here in this area, you'll notice that here's a 1016 line again, and then a 1012. And then inside the 1012, you have a 1008. So here, the air pressure seems to be going from 1016 to 1024. It's increasing. Wonder what that means. And then over here, it seems to be going down from 1016 to 1008. Well, let's use isobars to help us see this and see what it tells us. All right, so now these lines that you see on the map are called isobars. And when we connect these areas of equal pressure, you'll notice it does in fact form these circles. And as you move from the outer part of the circle to the inner part of this circle, the pressure seems to increase. This indicates it's a high pressure system with calm, more clear weather, which is why the sun's there. And then over here you'll notice, in fact, the pressure does go down from 1016 to 1012 to 1008, and so the pressure's dropping. This indicates it's a low pressure system, so air is going to be rising, possible, if there's moisture, possible cloud formations, possible rain, low pressure. And then the other thing, you'll notice these squiggly lines. What is that all about? Well, like we said, just like in the balloon example, Air wants to move from areas of high pressure to areas of low pressure. And so you could predict that there would be wind moving between these two pressure systems from west to east, from the high pressure system to the low pressure system. Well, that's it for now. I hope this video has helped you to understand pressure systems and how they affect our weather, and a little bit about how we measure pressure systems. We're going to talk more about this in class, and we're going to have some really cool pressure demos. Can't wait to see you guys. Talk to you soon.